When I see you next, we are going to go through 2 free response problems in class that we're going to grade and put in the grade. Okay. So in front of you, we have a problem that we're going to break up piece by piece, sort of like we did when we did that write in, write out stuff. Okay. More than likely, one of your 6 free response questions will deal with either a slope field, something that you're going to need to do separation of variables on, or some sort of initial condition, interpret it. Okay. So we need to make sure that we are ready to go. So what I'd like you to do is I want you to read through what's in this, just read through the whole problem, just kind of get an idea of what's going on here. Okay. All right. So this is a little bit different than what we experienced at the end of unit 4 when we did those rate in, rate out problems, because our derivative, dw dt, has a w in it. So this would be like dy dx equals 1/25 y minus 300. Okay. Let's notice that w is an increasing function. Okay. And it models the amount of total solid waste stored at the landfill. Okay. And this is for the next 20 years. T equals 0 represents 2010. Okay. This is from the 2011 exam. So that's why they're using those years. Okay. So part A, use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste at the landfill in the first 3 months. So if we're talking about years, that means t equals 1/4. Okay, so dw dt is, what is it, 1/25 w minus 300. Okay, that is our dw dt. Oh, there's parentheses there. Okay. When time is 0, what is w? At the beginning of 2010, a landfill contained 1,400 tons of solid waste. Okay. When time is 0, W is 1,400. So if I'm asking you for the tangent line to the graph at time is 0, first of all, we need our slope and we need our point. Okay. So if time is 0, W is 1,400. That's our coordinate. Okay. To get the slope, we need to actually plug our coordinate into the derivative. So if W is 1,400, plug that in. What is the value of the derivative? Okay. Let's also talk about labels. W is 44 tons. dw dt, what would that label be? Ooh, tons per year. Okay. So let's remember how to write the equation of a tangent line. Okay. Normally we would have y minus y1, don't write this, slope times x minus x1. People, we don't have x's and y's. Instead of y, what's our variable? W. So this is going to be W minus 1400. Okay. Our slope is 44. And instead of X, we have T. T minus E. Okay. Now, do you need this minus 0? No. And if you wrote this as W equals 44T plus 1400, nobody's going to be upset. Okay. So now let's use that. If we plug in 1/4 for T, what is W?
1,400.
Does it make sense that that value is higher than when T is 0? Why? W is an increasing function. Thank you. Okay. All right. On the backside, part B. Find the second derivative and use the second derivative to determine whether our answer in part A is an underestimate or overestimate. Okay, so first of all, let's find the second derivative. If our first derivative, dw dt, is 1/25 times w minus, what is it, 300? Okay. What's the derivative of this? Okay, what if I wrote it like this? dy dx equals 1/25 y minus 300. Okay, yeah. If we were to take, we could like distribute that, right? This doesn't matter. When we take its derivative, it's going to go to 0, right? But 1/25 times y, that derivative would be 1/25 dy dx, right? So when we take this derivative, we're going to have 1/25, not dy dx, dw dt. Okay. So we have 1/25 times 1/25 w minus 300. Okay, so from time is 0 to time is 1/4. First of all, what was W when time was 0? 1400, and we know that W is increasing. So if W is 1400 and gets bigger, what is true about our second derivative during that time? It will always be what kind of number? So our second derivative is positive. Second derivative being positive means we are concave, which means we are what kind of an estimate? Underestimate. Honestly, if I were to choose a area response problem, my number 1 choice would be area volume. My number 2 choice would be one of these. Okay, because of this third part down here. Okay. When we do separation of variables, you have an opportunity for like 5 points, and it's not difficult math. Okay. So in part C, we're going to find the particular solution to our differential equation with that initial condition 0, 1400. Okay. And this is what they're looking for. They are going to look for that you separate variables. All right. How do we separate variables? Okay. I'm going to put W minus 300 over here. and I'm gonna keep 1/25 over here with the dt. Remember how I tell you, keep the coefficient on the right side. Okay, that's gonna be 1 point. Then you need to actually integrate both sides. So we have the natural log of the absolute value of w minus 300 equals what? Is that better? I knew what I needed to get to and I just didn't write. I'm so sorry. 1/25 t plus c. In this free response problem, you are either going to get 1 point for both antiderivatives or 1 point for each antiderivative. It depends on the problem. You're also going to get 1 point for giving the plus c. Okay, so far that's 3 points. We haven't really done a lot of work yet. Okay. Okay, now we need to solve for w and use our initial condition. That's where the other 2 points out of the 5 are going to come in. Okay, 5 out of 9 points just for doing this kind of problem. Like, this isn't terrible. Okay, so we've been solving for w first and then using our initial condition. So how do we do that here? So we have w minus 300 equals c e to the 1/25 t. Are you okay with me going straight there? Because this is e to the 1/25 t times e to the c, and e to the c is still a c. So we can add over that 300. And I really like when our initial condition is when t is 0. Because when I plug in 0, e to the 0 is 1, and our c value is 1100. So w equals 1100 e to the 1/25 t plus 300. So let me count through those points again. You would have gotten 1 point for separation of variables, 1 point for your antiderivatives, 1 point for the plus c, 1 point for using your initial condition, and 1 point for solving for w. I just think that's so crazy. Okay, I think the hardest part of this problem would be in parts A and B, just working with a derivative that wasn't dy dx. Okay, we had to really think through w is the same as y, x is the same as t, and really think about how that plays into finding the second derivative, writing the equation of the tangent line. Okay. So I don't see you until